Hey guys, so in this part we will just quickly run through few root locus plots. I will just run you through 3 or 4 problems just to tell you how to use those steps. Okay, so this is the first problem. G of s is okay. All through again I assume that everything is a unity feedback system. So, do not really worry about what is happening to the h, and then I just get the k in here as well. So, okay, so let us try plotting this. Okay, so I have m equal to 1, n equal to 3. So, there n equal to 3, so I will have 3 branches, right. So, 2 starting from the origin here, I have a pole at -9 and I have a 0 at -1. Okay, this is not drawn to scale, so that should be okay. And this is again the sigma and j omega. Just draw one. Okay, these are the 2 roots at the origin. Okay, so first thing is, well, there are 3 poles, 1 0, the root locus will have 3 branches. It has 1 0, so one of these pole will go to a 0 and 2 of them will go to infinity. We need to find out how these 2 guys go to infinity. Okay, so first is we need to like step 4, we need to find out what is sigma a, or the centroid point of the asymptotes. So, that is just like, okay, you get -9 and then the zeros are here, minus of -1, n minus m is 2, so this will be -4. So, somewhere here is my centroid point, again not drawn to scale, but okay, somewhere here. Okay, and then okay, so what are the angles of these asymptotes? Angles of asymptotes, we compute them as 2q plus 1 times 180 degrees over n minus m, that is 2. So, that will again give you plus minus 90 degrees. So, somewhere in this direction, vertically above and vertically downwards. Okay. Now, other thing which we need to look at is do the roots cross the imaginary axis. Okay, so I just write down the characteristic equation of 1 plus g of s equal to 0, and this gives me that s cube plus 9 s square plus k times s plus k equal to 0. And let us see when does this actually meet the imaginary axis. So, I just quickly draw the Routh table. So, I have s cube, s square, s power 1, s power 0. So, s cube I have a 1, I have a k, I have a 9, I have a k, and what comes here is 9 times k minus k by 9. So, that would be 8 by 9 times k. Okay, so for what values of k this goes to 0, okay, k equal to 0, this guy goes to 0, but if I substitute k equal to 0 over here, I see that, well, there are no real there is no other point apart from the origin that it meets, that the root locus actually meets this j omega axis. So, the roots, do the roots cross the imaginary axis? The answer is no, and it is just obvious from this table here. Okay, now the breakaway points. Right, so, what do? We just take dk by ds, we equate it to 0, right. I will not do, okay, this I think that should be easy to compute. So, we will have s equal to 0, s equal to -3 and -3. Right. So, so one of course, you can see here, right, there are already a breakaway point because there is multiple root here, and then you have 2 guys sitting here at -3. Okay. So, this is how it looks like. Now, okay, now we have to decide, okay, how do these guys move from here, which direction they go, do both of them go here, both of them go here, or they just go around, wander here for a while and come back. I know that they never go to the right half plane because of this Routh criterion. So, they just have to be somewhere in the left half plane, And how do they go away? Well, they go away from here at an angle plus minus 180 by r, where r here is a number of the roots. So, there will be plus minus 180. So, the initial moving point will be like, so the tangent would be here, right, plus minus 90 degrees, and then these two guys go here, and then they have to arrive here, right, arrive here through some, so just arrive at this point. And look at this guy also. So, this guy has, okay, so even before that, I think what we forgot is to see what point of, or which part of the real line is on the root locus. So, I start from here. What about the area between 0 and minus 1? I just look at my right, I have 2 poles, but this number should be odd. So, this area is ruled out. I go from minus 1 to minus 9. I just look at the right, I have 1, 2 and 3. So, this entire part is on the root locus, okay, the part from minus 1 till minus 9. Okay. So, I know that, well, these two guys will move away from each other and they will arrive at this point minus 3. Okay. Now, where does this guy go? This guy moves to the right, because this is on the root locus, and this guy also moves and it also arrives at this point, because you have 2 times minus 3 coming in. Okay. Now, these guys go away at plus or minus 180, and again now look at how, so there are 3 roots coming in and 3 roots will go away. So, I just use the angle criterion. I have 180 by 3 2q plus 1. So, that will give me 60, 60 and then 180 and then 300, right. So, this is 60, this is 180 and this is 300, or even minus 60, right. So, this is 60 and minus 60. So, here the roots will arrive here this way, and after they come here they just go away to infinity like this along the asymptotes which are given by this at minus 4 plus minus 90 degrees. So, I just try to join the dots here. So, I will have a root locus which looks like this from here and so on. Okay. So, all the steps are clear, right. So, this is how it goes. So, I start, so it's okay. So, this is okay, I just do not draw further to the left because there is nothing happening there. So, there are 2 roots here, they go, they meet at minus 3, which is the break in and break away point, right. So, just roots break in here and they also go away from here, and then there are 3 guys which come in, 1, 2, 3, and then they go away here, here and here. One pole is going to the 0 here, the remaining 2 poles are going to infinity, right. So, that is just following all the steps as before. Okay. So, the second guy. So, here I have 2 and 1 3 zeros, and I have 1, 2, 3 or 5 poles. Okay. So, 5 poles would mean 5 branches. Okay. So, let us just locate these poles and zeros. So, I have a 0 at minus 1, and then this is the 0 at 0.1 plus j6, another 0 at minus 0.1 minus j6. Okay. Now, these two will tell me that there is a pole. Again, I am not drawing to scale, but just to make this a little more visible, 0.1 plus j 6.6, and here is okay, it will be minus 0.1, minus 0.1, minus 0.1, minus 0.1, minus j 6.6, and somewhere here is my origin. Okay. Sorry, this is my origin and these are my poles, right. So, this distance is 0.1. Okay. So, and then additionally there are 2 poles here at the origin. So, we have 1, 2, 3, 4 and one guy is sitting here at minus 12. Okay. So, 5 poles and 3 zeros. Okay. So, the root locus will have 5 branches, 3 branches will go to these zeros, 1 0 here, 1 0 here and 1 0 here, and then there would be 2 of them going to infinity. We will find out how they would go to infinity. The first question we would like to ask is, well, which part of the real line lies on the root locus. So, I look at the region between 0 and minus 1. I do not really look at these guys because they do not really change the even or odd numbers, right. So, if it's even before, after them, it's if it's even before them, it will be even after them, and so on. Right. So, I do not really need to count this. So, I start from the origin here between 0 and -1, I just see 2 guys to the right. So, this is not allowed. Then I come here and I say -1, I just see between -1 and -12, I see 3 guys to the right. So, this entire region is on my root locus. Okay. So, one thing I know that this guy will move in this direction, right. Okay. So, then so I can just look at it and see, well, maybe this is a pole goes to 0, so maybe it just goes this way, right. That is a lazy way to look at it, from here, and this one to here, this one is going to infinity, and these 2 guys, I do not know, maybe they are just here, they just do not know what to do, and then they will go to infinity from here. That may not be true, because there are some other rules which we need to follow as well. So, I just remove this, and then I remove this. Okay. So, let us see the, well, let us say the angle of the asymptotes. Angle of the asymptotes, well, you could easily compute them to be plus minus 90. There are 2 guys which are going to infinity. Okay. The centroid of the asymptotes, sigma a, that would be again for all the poles is -12. I have a minus, again I just take all the real parts, if you remember how we derived these things, minus the 0 here, which is -1, and then the real parts of the poles, 0.1 minus 0.1, everything divided by n minus m, that is 5 minus 3, and this will give me a centroid point of 12 and minus 11 by 2. Okay, so somewhere here 5.5. This is my sigma a, right, minus 5.5. Okay, so the next thing I would like to do is the angle of departures from, well, let me say this pole, minus 0.1 plus j 6.6. Okay, so I need to look at the angles which these 2 guys make here, right, and then I need to look at the angles which these guys make. So, let me call this zeros as, let me call this as psi 1, the angle made by this 0, let me call psi 2 by this 0, and then psi 3 by this 0, and then I have 5 poles, right. So, let me call this phi 2, phi 3, phi 4, okay, this is the zeros, and then so the angles of departure, and I just need to compute first what is phi 1, and then phi 1, okay, so is all these angles, right. So, I will just say angle by all the zeros minus all this phi 2, because there is no angle contribution from phi 1 to itself, phi 2 plus phi 3 plus phi 4 plus phi 5. Okay. And then to just get the angle of departure, what I do is I just add an angle of minus 180 degrees here, right. Okay. So, let us compute each of these angles. So, I am just looking at the 0 starting from psi 1, and from here till here, if I measure the angle, that will just be plus 90. So, I have a 90 plus what is psi 2. Okay, let us do psi 3, that is easier, right. Psi 3 would also be 90, and then this angle would be the angle over here. So, that is the inverse tangent of this distance, that is 6.6 divided by the horizontal distance, that is 0.1 or 1 minus 0.9. So, that is 0.9 or 0.1 minus. So, this one, and then minus we have the angles from phi 2 is very nearby. So, I could as well approximate this by 90 degrees. So, phi 2 would be 90, phi 3 would also be 90, phi 4 would also be 90, and then I have this guy. So, that is inverse tan of from this 0 again. So, that is 6.6 by the horizontal distance 11.9, and all of this minus 180. So, that will give me an angle of 142.6. So, now I know that from here I am actually going this direction. Okay. Similarly, I could also compute what is the angle of arrival here. The angle of arrival here would just again depend on, well, this angle, again all the other contributions, right, and that we could easily compute again just by doing all the same things to be similarly about minus of 142. So, just arriving from here at an angle of minus 142 approximately, right. So, because there will be some little change because of this 0.6 number. Okay. So, I know that, so this guy is not directly falling onto this directly here, he is just taking a little detour and coming here and doing this. Similarly, this guy also will do the same, right. This is also should be easy to compute, this and this. Okay. Now, what happens to these guys? So, this guy I know goes and sits up here. So, we need to compute what are the breakaway points. So, breakaway points could be computed by just looking again at dk by ds is equal to 0. Okay. So, again it is just a little complex expression here, but okay, this will give us some points, and let us see how the final plot looks like. So, what we would expect is, of course, there will be one breakaway point here. These guys should meet at some point and then go to infinity along asymptotes given by this one. Okay. So, the plot would say, well, there is a breakaway point here, there is a break-in point here, and then so let us look at each of these routes. So, this is easy to find out. This guy goes here, this guy goes here, these two poles, well, this guy goes here, this guy goes here, this guy travels here, and then they come here, and then they just go away this way to infinity. Right. So, this is the point minus 5.5. Right. So, I am just avoiding computing this one because okay, it will just be a little too ugly to write down these expressions, but we could compute. So, the idea here is to just the complexity here is not to blindly say that this guy will just directly fall onto this guy and this guy will just directly fall onto this guy, right. So, they will actually follow a different path like this and like this, okay. And then the rest all is just a computational procedure. You just do dk by ds and then equal to 0, and then you get this plot which looks like this, right. Okay. This is a little ugly here, but then okay, we have to draw it by hand. So, it looks a little distorted, but this is more or less how the plot actually looks like. Okay. The other example. So, again I have all, and again a unity feedback system. Okay, let us see where my poles and zeros are, and I start by drawing this diagram here. So, I have again a pole at origin, a pole at minus 2, and then I have a pole here, right, minus 1 plus j2 minus 1 minus j2. So, m equal to 0, n equal to 4. Okay, so, which part of the root locus lies on the real axis? There is one pole at the origin. So, I look here from the right. So, then this entire line lies on the root locus. Okay, so this entire thing. So, these guys will just mark that these guys will travel this direction. Okay, so what is the next thing over here? Then you have to compute the angles of asymptotes. angles of asymptotes, again like 4 of them. So, you will have 180 by 4 and then you keep adding 45, then you have 135 and you have minus 45 and minus 135. Okay. And then you are also looking at the center of the asymptotes, sigma A is okay, you can just check that this is minus 1, right. I am skipping all this computation. So, this is your center of the asymptotes, right, and then they go this way and this way. Okay. So, this is like 45, this is minus 45 and so on, 135 minus 135. Okay. So, let us see where this guy goes, angle of departure from minus 1 plus j2. Okay. Okay. So, what are the angles I am interested in? I am interested in this angle, I am interested in this angle, and I am interested in this angle. Okay. So, that phi angle of departure is just the negative, if all are poles, it will just be negative 2 over minus 1 for the first guy, then you will have minus tan inverse 2 over 1, this guy is at 90 degrees and then I add 180 degrees from the formula and I get all this will just add up to minus 90. So, this guy will just vanish by itself because you can also see the symmetry here. So, this guy just vanish. Okay. So, one thing I know is from here I am moving here, right. Similarly, I can compute here that I am just going here and then I am just moving this way, right. So, if I am moving this way I just keep moving this way and I see that well something like this happens, right, that the entire line between minus 1 plus j2 and minus 1 minus j2 is on the root locus. This is the angle of departure from minus 1 plus j2. Here I can compute easily, right, it is just be minus 1 from minus 1 minus j2 would just be plus 90. Okay. So, this is something interesting happening here, right. So, everybody is meeting here, well that is what it seems like, right, and then what do they do after they meet here? Well, now let me compute the breakaway points. Again by setting dk by ds equal to 0. Okay. So, this means I will have of course one breakaway point at minus 1 and I will also have breakaway points at minus 1 plus minus j 1.22. So, this is 2, this is 1. So, I am having breakaway points even here, something more interesting happening. This is 2, this is 1 here and I am having at 1.22. Okay. So, guys come here, they even go away. Okay. So, this guy comes here and then maybe then it seems that this guy will go and these two poles will meet here, right. This guy goes here from here till here and they meet here. This guy goes from here till here and then this guy they meet here. Okay. So, something strange is expected to happen here. Now, look at even the asymptotes, right, they look as if this might actually come here and then cross the imaginary axis. So, does the root locus cross the imaginary axis? Well, I just look at the characteristic equation, right, and then I am looking at the Routh criterion. So, my characteristic equation turns out to be 4 okay, sorry. Okay. So, just computing characteristic equation again from 1 plus g times s equal to 0, I have a characteristic equation which looks like this, s4 plus 4s cube plus 9s square plus 10s plus k equal to 0. And I do again the Routh table and what it gives me is that well there is again k at a number 16.25. I will skip all the details, by now you should be experts in computing these guys, and also at an omega 0 of 1.58, right. So, they cross the imaginary axis at this point, say, okay, I am just drawing approximately, again not to scale, this is 1.58 with a minus sign, this is 1.58. Okay. So, now I know that, okay, it seems two of the roots will cross the imaginary axis. So, let us again try to analyze what is happening. This guy is going here and well, it is a breakaway point. So, he is just waiting for somebody else to come and meet him here, so that he could just say hello and go away. Similarly, this guy starts here, there is again a breakaway point, right. So, these are this complex breakaway points. Okay. So, these guys come here and this guy also comes here, they meet, right, and then say, well, okay, we have to go away because it is a breakaway point. So, this guy comes here, he goes and then they meet here, right. After this, well, they decide, okay, where should they go? They should go asymptotically along this line, right. So, this is this way, this guy will go, this guy will go this way, right, again at angles 45, minus 45 and so on. So, to the asymptotes, again this will be like this and this will be like this, sorry. So, I am just messing up the scale here, but the point where it meets the imaginary axis is at this omega naught, which we computed from the route table, this is 1.58. Okay. So, I will just show you how the plot now looks like, right. So, this guy comes here, goes here, this guy goes away here, this guy goes away here, this point is 1.58, this point is minus 1.58, again this guy here, here, this and this, right. So, we are just using all those steps to just see the entire plot, right, and then see this intersection with the imaginary axis. So, I know that after some point, if I keep increasing the gain, the system might actually go unstable. It is not might, it will actually go unstable after my gain increases to beyond 16.25, right. Okay, you could just do this on MATLAB. I will shortly post a little tutorial for yourself to see how to use MATLAB to get these basic plots, other plots like the step response, how to give a command for the transfer function, find the poles and zeros and so on, right. So, I will just post a little tutorial on that. I will not do it in the class over here, but that tutorial would be self sufficient for you to learn by yourself. Okay. So far things were nice, right. So, if I give you a block diagram which looks like this and I say for the system given, plot the root locus as this guy k1 is varied from 0 to infinity with this parameter beta being equal to 2, and then this should be 5 here, repeat with beta equal to 5. Not only that, then I say I keep k1 fixed, right, and then I vary beta from 0 to infinity. Okay. So, how do I handle this? So far everything was given to me that g of s was k in the numerator, some zeros here and then denominator. Okay. So, how will I do this? So, first is I need to get the characteristic equation. Okay. Now, given this guy, do I know anything which I learned in the past that would directly give me the characteristic equation, right. So, for that I will do the signal flow graph analysis, right, where the transfer function had 1 over delta plus I think summation p k delta k or something, right. I do not really need to do the entire transfer function. What I just need to know is what is in the denominator of the transfer function, right. The characteristic equation, what was it, 1 plus g s h s, if I had a k outside, this was 0. This is just a denominator of the closed loop transfer function. Okay. So, first let us draw the signal flow graph of this. Okay. So, the signal flow graph would look something like this. So, I have 1, a 5 and 2 over s plus 10, then I had k 1 over s plus lambda, and then I had 1 over s with a 1 and a y. Right. So, this is, so you have R 5 2 over s plus 10 k1 over s plus beta and so, okay. Sorry, I called it a lambda here. So, let us erase that and put a beta. Beta. Okay. So, what happens after all this? So, I have after this guy, I have a loop of -1. From here till here I have a gain of 0.1. This is plus or minus, okay, it is plus. Okay. Then later I had s plus s over beta, I had a 0.2 here, and here I have 1, and here I had 1, right. And now these are all the directions of the arrows. Okay. So, I am just interested in finding the overall delta. So, not really the transfer function, because I know that I am only interested in the denominator, which I call the characteristic equation. Why is that? Because I am just interested in how my poles, or how the poles of my closed loop system vary as I change a parameter from 0 to infinity, which is k1 in this case. Okay. So, the delta here is 1 minus, well, you look at all the individual loops. There are 3 loops here, right. One loop, okay, this arrow is here, one loop is this one, second loop is this one, and the third loop is the outermost loop. Okay. So, the delta turns out to be 1 plus, I just look at this one, right. So, I have 1 over s plus 10 plus, I look at the other guy, this one. So, I have 10 times k1 over 0.2 sorry, something is wrong. So, 2 times k1 over s plus 10 s plus beta, and this take the 5 and 0.2 just becomes 1. So, that just goes away from here, and then the last term. So, I go the entire distance here, I have 5 and 2 10 times k1 over again. So, I have s in the denominator, s plus 10 s plus beta. Okay. So, this equal to 0 is my characteristic equation. So, if I want to draw the root locus in terms as with k1 as a parameter, I need to get the equations in the form 1 plus k1 times something in the numerator polynomial a of s, something in the denominator polynomial b of s equal to 0. Okay. So, it should look something like this. Okay. Now, can I rewrite these equations that way? I just do some manipulations, and what I get is, so first let us see. So, this will become 1 plus s plus beta plus twice k1 times s plus 10 k1 over the entire denominator s plus 10 s plus beta is 0, okay, which I could also write as this is equal to s plus 10 s plus beta plus s again this entire thing s plus beta plus twice k1 s plus 10 k1. Okay. So, this will further simplify into s plus beta s plus 11 plus twice k 1 s plus 5 equal to 0, which I could also equivalently write as 1 plus twice k 1 s plus 5 over s plus beta s plus 11 equal to 0. Okay. So, now I have well, I can just do this, right. So, I have, assuming beta is always greater than 0, I have a 0 at minus 5, I have a pole here and a pole at minus 11, and then depending on wherever the beta is, I will have the location of the other pole. I will just do the simple one for myself. So, beta equal to 5. So, I will have a pole also here. So, this guy will just go away. So, there will just be nothing here. So, I will just be left with a transfer function which looks like 1 plus twice k 1, this guys will cancel out, s plus 11, and I easily know how to draw the root locus for this, right. I am not going to do into the details of that. Okay. Now, when k is fixed and lambda is varying, right, I just again look at this entire expression, and now I want to write it in the terms of a transfer function of where 1 I have 1 plus lambda some other polynomial a prime s divided by some other polynomial b prime s. Okay. So, again I can write it down in a fairly straightforward way again, right. So, I just start from here. So, I just skip a bit of the computations, but I will just have s plus 1 over s square s plus 11 plus 2 k, where k is a fixed value now according to the problem statement. Well, you can just say any, just take k 1 equal to 1, and now I can look at what happens to the root locus when now lambda varies from 0 to infinity, keeping k into fixed, keeping k fixed. So, the idea is to just write down this characteristic equation in this form, 1 plus lambda a prime by b prime being equal to 0. I will skip the steps, because now the looking at the steps of the root locus should be kind of very straightforward now, right. So, those steps, okay, sorry, it's a beta and beta. Okay. Okay, I'll do this again. Okay. So, we will now see how to draw the root locus with beta as a parameter, or in other words, I want to write the characteristic equation as 1 plus beta a prime s over b prime s equal to 0. Okay. So, I just go from here, I just skip the computations here. So, I just have 1 plus beta s plus 11 over s square s plus 11 plus 2 k s plus 5 equal to 0. So, for a fixed k, I know what will be the poles here, I know what are the open loop zeros, and I could just say as beta going from 0 to infinity. I will skip the steps because these are just the routine steps, just to give you an idea of how to formulate a problem in a way that I could use the root locus techniques directly. It was not very obvious from here, because so far all the problems were very nice, right. I was just given g and h and a k, and I just had to do. If it is a little complicated, there is nothing really to worry. I can just look at my signal flow graphs and then just compute the delta, which is a denominator. I do not even really need to look at what the numerator is, right, because I am just interested in the characteristic equation, which is essentially the denominator, right, and then okay, the steps will follow. So, I just stop here, and I will leave these things for you as an exercise to do. Okay, thank you.